Hello guys, welcome back to Maths Zone African Motives. Still on our engineering science N2, and this is our question paper which was written in November 2023. For those who wrote this question paper, we shall have a revision. But if you are sitting for another exam, it's fine that you have the basics of what is required, and you know how the questions are going to be like if you're writing in April, if you're writing in August, if you're writing in November. These are the same typical questions that you are going to have at the end. All right, so we shall quickly rush through our questions. Like I always say, that make sure that you read your instructions and the information that we are given here. All right, answer all of the questions, read all the questions carefully. And what is important is that on your calculations here, all calculations should consist of at least the following 3 steps. All right, the formula that you're going to use, or the manipulation thereof, the substitution of the given data in the formula, that is the values that you're given corresponding to what you're given in the formula, and the answer with the correct SI unit, and also to use this where it is possible. All right, then let us quickly have this. As you can see here, we just round off on completion of each question. Round off to our main decimal places. We are not given to round off to our main decimal places. You can see, so we shall just maintain. You just maintain the one that you want if you're not given. All right, as long you are rounding off your answers at the end. All right, so the first question was on dynamics, and the 1.1 is define the term acceleration. The term acceleration. All right, so as we understand this, acceleration is simply the rate of change of velocity. So this is simply the rate of change. That's the rate of change of what? Of velocity. All right, the rate of change of velocity, which is simply measured in what? Meters per square second. As we know, velocity is the rate of change of displacement, but acceleration is taken from the velocity now. Okay, then 1.2, we are given that a car is traveling at 36 kilometers per hour for 8 seconds when it begins to accelerate. When it begins to accelerate. Okay? At 2 meters per square second for 16 seconds. This is what we are given. Determine the following. 1.21, the initial velocity of the car in meters per second, and that is 1 Mach. So we are given the car is traveling at, that is the initial velocity that we are given. It is traveling at that velocity. All right, so that's 1.2 in this case, so the initial velocity, which is 36 kilometers per hour. But we are supposed to have this in meters per second as per our question. If you check from your formula sheet, if you are given that 1 meter per second is equal to 3.6 kilometers per hour. So we can use this as a conversion to convert this to meters per second. What is going to be the equivalent of 36 kilometers per hour in what? In meters per second. So we have to simply divide what we want over what we are given. So we are simply going to divide this by what? By 3.6. So if we divide this by 3.6, you shall obtain 10 meters per second. Remember, we are converting to what? To meters per second. Is this part over this multiplied to 1 meter per second. So it's simply 36 over 3.6 times 1 meter per second. So your answer is going to be in meters per what? Per second. That is the idea of the question there. All right. Then on 1.2, they're now saying the final velocity of the car in meters per second. The final velocity. All right. If you check here, this car actually had, or it moved in 2 stages. The first stage, it was traveling at this 36 kilometers per hour, which is the 10 meters per second for 8 seconds. Then when it begins to accelerate at 2 meters per second, there is now an acceleration after that for 16 seconds. So it's like in stages. So the best way that we could have understand this is by just having a sketch. Yes, it's true that we're going to have that part of the sketch later on, but it was just important just to have a sketch a little bit like this. This is our velocity here in meters per second, and this is the time in seconds. So if we check, they are saying the car is moving at this velocity, which is the initial velocity for 8 seconds. So what it tells us is that this is a constant it's a constant velocity. There is no acceleration at that moment. For the first 8 seconds, there was no acceleration. The speed, the velocity there was the same at 10 meters per second. But after the 8 seconds now, this car started to accelerate at 2 meters per square second for how many seconds? For 16 seconds. So meaning to say, for 16 seconds, there is an acceleration. For what? For 16 seconds. So meaning to say, for these seconds that are remaining, the 16 seconds, if we add 16, 8 plus 16, if we add 8 plus 16 seconds, it means we are going to end up at what? At 24. All right, is that so? So meaning to say, this here is going to correspond with 24. But we do not know now the velocity that is going to correspond here. We do not know the value of this velocity. That is the final velocity they are referring, or that they are talking about there. Okay, so if you just have this in mind, or just have this as an idea of what is happening, it helps you to know that this point is still at 10 meters per second. We are still at the 10 meters per second. So that is our initial velocity in that case. All right, so we have got the initial velocity, which is still at what? At 10 meters per second, the one that we had. We are still at 10 meters per second at this point. But it is accelerating now. We are given that acceleration as 2 meters per square second. Remember, we are given this acceleration, 2 meters per square second, but we do not know the final velocity. Given the time when this acceleration took place, the acceleration took place in how many seconds? 16 seconds. So we have the time there in between. The time is what? 16 seconds. What is going to be the value of what? Of V. That was the question. What is going to be the value of V? All right, so if we check from our formulas, we have got this formula that connects the final velocity and the initial velocity with the acceleration and time. V is equal to U plus AT. From this formula, we can play around and say, okay, we want V. We have got the initial velocity, we have got the acceleration, we've got the time frame that was taken, which is 16 seconds. So we can substitute here. V is equal to U, the initial velocity 10 plus the acceleration, which is 2 times the time that was taken. So this is going to give us what? The final velocity. That is the final velocity. So this was going to be 42 meters per second. All right, that is 32 here plus 10. That is 42 meters per second at the end. We are working with the second part of our diagram, this part here. All right. If you understand this, just to have this in mind, it helps you to answer this type of a question. I'm not saying you're supposed to draw the diagram, but it's good that you have it. All right. Yes, now they want us to draw that diagram on 1.23, draw a fully labeled velocity time graph. That is 3 marks for that. All right. So if we are to check, we are going to have a velocity time graph of this nature. I'm not going to have this up to the standard, guys. I'm just going to have this way. But you're supposed to have this properly drawn according to your scale. We said this is going to be 8, 24, and this is at 0 here. Now we have got the value of V. Remember, we calculated this V. Our final velocity is what? 42. So this is going to correspond at 42 according to your scale. This must be 42. Maybe you're going to use 10, 20, 30, or you're going to use 2, 4, 6. I don't know the scale that you're going to use, but you must draw this properly, something of this nature. All right, check the video on the dynamics on a separate question. I think there I explained as much there, so that you can at least have more information if you want to understand. But that is how you're supposed to have your diagram in that case. All right. Now from that, they are saying from that same diagram, which is the velocity time graph that we you have drawn. Determine the displacement of the car. From the same diagram, we need the displacement. All right, so that's 1.24. So the displacement, if we are working from the diagram here, the displacement, we are simply taking this as the area that we are having under the graph, under where this part, this one, this is the area under the graph here. All right, this portion under the graph where the object is moving here, it moved on this path. So the part that is under this one is the one that gives us the area, that gives us the displacement, which is what? Which is the area. So you're simply saying the displacement is equivalent to what? To the area under the graph. That is the idea there, all right? So displacement, remember, is equivalent to what? To the area under the graph. All right, so that is the condition. Do not take this part on top. You consider what is below. So if you consider what is below, there are two shapes that we can properly see. We can work this in many ways. All right, I explained the use of a rectangle and a trapezium in the last, in a separate video where I described this dynamics. So I'm gonna explain this way this time. I'm gonna take this way, this rectangle, the wall of this to the end. I'm gonna go with this up to the end of the triangle, up to the end of the shape like this. I'm going to formulate a rectangle like this. All right. It means I have formulated a rectangle. This one, it's a rectangle there. Then what is remaining here? It's a rectangle. If you check here, I'm remaining with a rectangle. So I'm just going to take these two shapes. I explained the other way of a trapezium in another video. So please check that video so that you'll be able to see other ways. All right. Let me explain this way so that we have got different ways. All right. So in this case, I'm going to use the area of the rectangle, this one, the first shape, and the second shape, which is a triangle. So the area of a rectangle, which is the length times the width. All right. So let me just put it this way. That is the area of the rectangle. Like I said, length times the width plus here we are remaining with a triangle, which is a right angle triangle on top, the second shape. So the area of a right angle triangle, half base times what? The perpendicular height. So the length times width, we are referring to this side, 24. And from here to here, it's what? It's 10. So that's length times the width. So it's 24 times what? 24 times 10. So that's 24 times 10 plus half base times the perpendicular. So yeah, we are asking ourselves to say, from this point here up to this point, how many units are there? That, remember, that was our second phase, from 8 up to 24. Remember, that was our 16. We are told that here it's 16 seconds. So this whole part is 16. Then what about here from this point here up to this point at the end, this one? We need this height. This is our perpendicular height. What is this value? So we subtract. This is 42. This is 10. The difference between these points is the one. We do not take the whole of the 42 because 42 is from the ground up to this point. As we want this part alone, this one that I'm indicating here, this is the one that wants this distance. So it's the difference between these 2 points, 42 and what? And 10. So that's if we subtract here 42 minus 10, what are we going to obtain? That's 32. So here we've got 32. Remember here we had what? 16. Here it was 16. So meaning we've got 16 and this is what? 32. So that's half of the base, which is 16 times the height, which is the difference that we have between 42 and what? And 10, which is 32. So that is the idea there. Okay, so this was going to give us the area. All right, so if we multiply the first part, that is 24 times 10, which is going to be 240 plus half of the base times the perpendicular height, which is half of what? Half of 16 times what? Times 32. That was going to give us something like 256. And if we add these two, that is going to give us the total displacement of 496. All right, meters. So there are so many ways. We could have used, like I said, we could have used the trapezium concept, this trapezium like this, and this rectangle, so many ways. All right, I want you to work it out and try. Like I said in our previous class, that I want you to try this. So I think for those who tried, we got this answer, which is fine. But if you want, you can also use the other way that I explained from that class. All right, then The last part on this diagram is to find the average velocity of the car, which is 2 marks. So the average velocity, remember from our description or from our definition, is the total displacement over what? The total time. So we calculated the total displacement in this case of our car, which is 496. All right. So that's 1.25. So that means the average velocity now is going to be given as the total displacement over the total time, which is the total displacement that we got of what? 496. So that's 496 meters over the time frame, the time taken, the total time from 0 up to 24. Remember, we've got the first 8 seconds and the last 16 seconds. We add them. They gave us what? At 24 in seconds. So that's velocity in meters per what? Meters per second. So if we divide this, that was going to give us 20,666 and so on, which is going to be 667. If you round off to 3 decimal places, remember, you're not given the exact decimal place according to this part. So if you're not given, just going to use 3 decimal places. If you're given, you work with the one that you are given for that particular paper. All right. So that was our person in this case, which is, all right, which is from that diagram. All right. 1.3 is now another question on its own. It's different from this part. It's just a separate question. All right. So there we are given a scooter reduces its velocity from 30 meters per second to 25 meters per second in 0.5 seconds. All right. So we have got from a certain velocity from this to this, the initial to the final. So the scooter is reducing in terms of the speed is reducing, meaning to say there is a deceleration in that case. There is what? A deceleration. All right, so that's 1.3. So we have got the initial velocity where it started from which velocity? From 30 to 25. So from 30 is our initial. So 30 meters per second, that is our initial velocity to the final velocity of 25 meters per second. This was done, or it was taken in how many seconds? In 0.5 seconds. All right, so we're given the time frame in that case in 0.5 seconds. So with this information that we have, the question is determine the deceleration of the car, of the scooter in this case, the deceleration. All right, what would be the deceleration? The same way that you calculate your acceleration is the same way that you calculate your deceleration. So this is the case. So the deceleration from the same way that we calculate our acceleration. Remember, from our formulas, v is equal to u plus at. So from this, we can make a the subject, which is representing the deceleration in terms of this. So that will be v minus u. If we take this to the other side, this is equal to at. We want the value of a, so we divide by t. We divide by t. That means our a representing the deceleration as we are given on this question. We know that a represents the acceleration. So meaning to say we are going to obtain a negative value if it is what? A deceleration truly. So that is a is equal to the final velocity v, which is 25. So that is 25 minus the initial velocity, which is what? Which is 30 over the time that was taken of what? 0.5. Okay, that is over 0.5. So this was going to give us the acceleration. So our acceleration in this case was going to be negative 10 meters per square second. All right, so that is the value of a that we were supposed to obtain at the end. All right, I think we are together on this part. Then determine the distance traveled in 0.5 seconds. So the distance you calculate the same way that you are using to calculate the displacement from our formulas. Remember that S is given as that's 1.32. S is equal to UT plus half AT squared. We also have this one that is V squared is equal to, actually it's given as 2AS. They gave us this as 2AS is equal to V squared minus U squared. Is it minus or plus u squared there? But you still remember that we have got this formula. V squared is equal to u squared plus 2as. So this is exactly v squared minus exactly. It's the same thing. There's this formula also. So meaning to say here we can calculate our displacement. Just divide by 2a by 2a. That will be s is equal to v squared minus a squared minus u squared over 2a. That's another formula. We've got everything there. All right. So I'm going to also bring this formula into consideration. So let's start with this one and see what's going to happen here. So that's s is equal to ut. That is the u, the initial velocity here, which is what? 30 meters per second. So that's u, 30 in that case, 30 times the time. Remember, they said in 0.5 seconds. That is when we got this acceleration, the time is still the same, 0.5. So that's 0.5 plus half of the acceleration at that moment. That is -10 times the time. This is half 80 squared. 80 squared. Sorry for that, guys. That is the time squared, 0.5 squared, right? So always use the formula sheet, that can help you not to make mistakes. So that was going to give us 13.75. If you simplify properly, that was going to be 13.75 in meters. That is the total displacement, the total distance according to how the question was given there. All right, I talked about the other formula that I indicated there. Let's see if we are going to have the same thing. Remember, we said 2as is equal to v squared minus u squared. So if you want s here, we're going to divide by 2a by 2a. That means s was going to be v squared, the final velocity squared. The final velocity 25, that's 25 squared, all right, minus u squared, the initial velocity here. Our initial velocity was what? 30. So that is 30 squared. All right. Everything over 2 times the acceleration, the same acceleration that we got within the time frame of 0.5 seconds. That is where we got. Remember, here our time was 0.5. So this acceleration, it corresponds when the time was what? 0.5. So we are still at the same value of acceleration of what? Of -10. So that is going to give us the displacement. So if you check, guys, you have to apply your formulas properly. You have to use your formulas properly. That is for us to understand this concept. All right, we must do this properly. All right, are we going to have the same thing here? We're going to have the same thing. This is going to be 13.75 again. Yes, that is 13.75 meters. So I want you to try so many ways. You check the previous class, like I said, the previous video that I worked on. I explained other ways. I think there's another way that I also explained there. So this is how you answer these questions. All right. That was question 1, 15 marks on everything. Then let us move on to question 2, which was on statics. There we are given that on 2.1, name 2 conditions to ensure a beam is in equilibrium. If we are saying that a beam is in equilibrium, what are the conditions? All right, so there, remember, we talk about the issue of the moments. All right, so I'm just going to write in short, guys, but you're supposed to write this in full. Remember, we talk about the sum of the clockwise moments being equal to the sum of the anti-clockwise moments. We talk about the sum of the upward forces, the forces that are going up, equal to the sum of the forces that are going down. That will bring a beam to be in what? Equilibrium. So I want you to write that one in what? In words, okay? Please write it in words. On question 2.2, complete the following sentences by filling in the missing word or words. They are supposed to be either a word or it's words there. Write only the word or words next to the question number, all right, that were given from 2.21 up to 2.23. Right, if 2 forces acting on a point are represented in magnitude and direction by the 2, all right, so if we check, this is like, this is our parallelogram, this one, from the parallelogram of what? Of forces. So if we take from that, parallelogram of forces, remember, they can even ask you to describe this. So we know that this must be the magnitude and direction that is by the two adjacent sides. It is taken, it is represented in magnitude by what? By the two adjacent sides. It's magnitude and direction of the two adjacent sides of a parallelogram. All right. So this is 2.21. So that was the adjacent sides in that case. All right. The adjacent sides of what? Of a parallelogram. Then they are saying the of the two forces is represented. What is it? The resultant now. All right. So this is 2.22, which is now the resultant is represented in magnitude and direction by the what of the completed, the diagonal. This is the diagonal of the completed what? Parallelogram. All right. Like I said, this we are simply taking from what? From the parallelogram of forces. I want you to go through that and make sure you understand it as a definition on its own. All right, 2.2, consider the fig 1 and answer the questions that follow. So there we are given, that's our beam in this case, which is supported at L and at R in this case, given these values, and you've got X, 3 meters, 2 meters, and 2 meters. All right, then the I've got a force of 80 Newton, 140, and there it's inclined at an angle of what? 45 degrees. Okay, take note about that. So the question was on 2.21, calculate the following: the vertical component of the 90 Newton force. The vertical component of this force, we are supposed to present this as a vertical component. So how do we take the vertical component? This equivalent distance here is the same as this one. So how do we take that one? We simply apply from our vertical component, you know, from the opposite concept and the hypotenuse concept. The ratio there is for sine, and we know that from our SOHCAHTOA concept, the sine is the one that carries what? The vertical. So if you understand this, you're going to see that the vertical component is going to be the 90 sine of what we are given. So that's 90 sine of theta, which is sine of 45 degrees. All vertical components, all right? F of y is equal to what we are given and the sine of theta, okay? So that is 90 sine of 45 degrees gives us what we refer to as the vertical component in this case, and that was going to be 63,63961. So it's going to be 64. If you round off, it's going to be 640. That will be 640 there, which is just 64 Newton. All right. So there we've got a 63,64 Newton, which is the vertical component now. All right. So that was our question there. And the question here on the other part is 2.32. The distance x between the left hand support and 100 Newton force. The left hand support and the 100 Newton force, which one? This is the 80 Newton force, not 100 Newton. This one is a mistake there. It's just the distance x is between the what? The left hand support and the 100. So this one, it was just a misprint, all right, on typing there. It was supposed to be 80, and this one is between this left hand and this force of what? 80 Newton. So now we do not know, because if the memo comes, they might, because now it's not yet there, they might do the calculations using 100, because they say, do you see now these errors that happen? So we just hopefully they are going to maintain the 80 Newton force, the one that we are seeing here. So we do not know the error was here on having it as an 80 Newton, or the error was on this one. You see now, we do not know. So I'm just going to use what is on the diagram, the 80 Newton that we are given there. But I think this one we're supposed to have there. We shall have it as 100 if we another class, so that, but I want you to try it from the 100 Newton, because it's an error. We do not know the error the way it was. Is it this 80, which was supposed to be? So there you are supposed to just have one. So I'm just going to use what is on the diagram, the 80 Newton, all right? Not the 100. It is supposed to be between this is, okay, that is the distance x. I hope you understand me. All right, so how can we calculate this distance x? All right, we can use, okay, we are told here by taking moments about support R. Our moments are supposed to be taken about this R. All right. So moments about R in this case. All right. So taking moments about R, that is taking moments about R. All right, so that was our condition in that case. All right, so that's 2.32. Okay, so let's see. By taking our moments, remember we talked about this idea of moments that the sum of these moments that are in the clockwise moments should be equal to the sum of the anti-clockwise moments. So if we consider this on R in this case, this is our R, this one. Remember, we're taking from this. It means we shall consider other forces as they move towards what? Towards R. So let's start with L. Okay, how is it moving towards R? Remember, in the direction, this is the clockwise. This is how the clock moves. This is our clockwise. Then the anti-clockwise like this. That is the anti-clockwise movement. Okay, so let's consider this one, the 63,4, the one that we calculate the vertical as it moves back to R like this. Which direction is it, this one? This is an anti-clockwise. So it is under the anti-clockwise. The same as the 140, it is under the anti-clockwise. This is anti-clockwise. This is moving again in the anti-clockwise direction. But if you consider the support L as it moves towards R in this case, which direction is this? Take note, which direction is this? This is the clockwise direction. So it is the only one that is moving in the clockwise. The rest are in the anti-clockwise direction as they move towards the R. Okay, so like I said here, we do not know, was it the mistake on the diagram to use this as 80 instead they wanted to use it as 100? All right, but us, we're just going to take as what as 80 as it is on the diagram. That is what we have. All right, but I want you to also use the 80 and see, the 100 and see what is going to be the answer there. All right, so we saw that the clockwise moments is just going to be only one, which is L back to what? Back to R. So that is the force of L, which we are given. We have got the force there of 124,728 times the distance. Remember, it's force times distance, all right? So if we check the distance, there's X is involved there. So it means it's best for us to just open a bracket because X is also involved. So that's X plus from, we want the whole of this up to R. So if we take this X, we're going to remain with the 3, 2, and 2. We add that. That's 3 plus 2, which is 5 plus 2. That's 7. So it's X plus what? X plus 7 is equal. We do not have anything in the clockwise. That was the only clockwise that we have. So the rest are in the anti-clockwise. All right. We've got 63,64 back to what? To this R, which is that there's a distance there of what? 2 meters. So we multiply 63.64 times 2 meters. All right. We move on to another one that is following the 140 Newton back to what? Back to R. So that is plus 140 times the distance back, which is 2 plus 2, that is 4. So that is going to be a 4 plus the last one, which is the 80, which is this one that I said, if you are using a 100, you're going to use it as a 100. But there, like I said, as for me, I'm just going to take as an 80, the one that we have on the diagram. So it's 80 back to what? To R there, which is 80 times what? The distance, that is 3 plus 2, which is 5 plus 2, which is 7. So that's 80 times what? 80 times 7, force times distance. That is the idea there. We can calculate the value of X. Since we have formulated an equation, we have formulated an equation there. So you can calculate the value of X. All right, so this is it. I'm just going to leave this side as it is. Yes, you can expand your brackets, but I'm just going to leave as it is. 124.728 into X plus 7 is equal to, combine everything on the right-hand side, you are going to obtain 1,247.28. If you've got those mathematical eyes, guys, we can see that there's something common. 1,24728. 1,24728. The same numbers. They are the same there. The same numbers. So it means instead of you expanding brackets, you're going to have a lot of things there. Just divide by this. because these numbers are just the same. Only the decimal is the one that is here. The decimal is after 3 decimal places. Here we have got 2 decimal places after the comma, but the numbers, they are exactly the same. So divide and see what's going to happen there. All right. Instead of you to expand with the brackets, that will be x plus 7 is equal to, if we divide this, you're going to obtain a 10. So that's it. We can transpose the 7 this side. It becomes a negative 10 minus 7. We obtain what? A 3. So x was going to be 3, which is what? 3 meters. We have got the distance here between the left end and the 80 Newton force. The distance there is what? Is 3 meters, right? So if we were to use the 100, it means that we were going to have, let's see, let us just do it together. If we're having a 100, that is the only part that was going to change, is the only this one. We're going to have a 100 only here. All right, so let's just see what was going to be our answer if we used the 100, because the rest was not going to change. Everything was going to remain as it is. So it was going to be 124,728. You simplify everything as it was, but here this one now, because it will be from this, because like here I'm saying, if you maintained this question to say and the 100 Newton force, it means this one, it means when this is 100, it means the error was on the diagram. The diagram was supposed to be what? 100 Newton. Okay. So remember what I said. It's either the error was here to have it as 80, because our diagram there is 80. So this was supposed to be 80. So use 80. But if you take this 100, it means this was the error now on the diagram. That is where the error was. It was supposed to be 100 on the diagram. So it means where there is 80 on the diagram, we are going to put what? 100. That is what I'm just trying to say here. Where there's this 80, which will just have what? A 100 there. Only that part. Then simplify everything and see. We just want to see what is going to be the answer on that part. So that will be 63.64 times 2. All right, if we combine this, okay, let me just show you the screen. Let me just have it together with you guys here on our calculator, because I never used this 100. I just worked with 80. So I prepared this, my class, with 80, but I want us to see what's going to happen. That's 63. Yes, 63.4. All right, so we've got 63.64. 0.64 times a 2 in this case, all right, times a 2 plus 140 times a 4 like this, plus this is going to be 100 now times what? A 7. So if we check, gonna have this value 1387. That's 1387.28. 1387.28. This is what we are obtaining here. Then if we divide by this, all right, what was this? This one was 1247. All right. So if you check, there are different answers that you're actually having there. All right. So if we divide this by this number, we divide by this one that is on this side, this number here, it's gonna be 124.728 like this, 0.728. And you're gonna get 11, this. You see now the decimal that you're getting. Then you subtract the 7, just like what we had. If you subtract the 7, it's gonna be 4.122. So if you use this, your answer was gonna be 4.122 if you used 100. All right. So if you check a closer look, it simply shows us that the higher chances of having an error was on this one. It was supposed to be what? 80 Newton. As you can see, the answer for 80 Newton is an exact value. All right. So we do not know where the error was. So we do not know whether you were given free marks there or not. But there, it was an error on the presentation. Okay. On question 3, we are given energy and momentum there. A body with a mass of 300 grams. We are given the mass of what? Of the body. 300 grams convert to kilograms. That will be 0.3. If you divide by 1,000, remember a kilogram is equal to 1,000 grams. All right. It is released freely from a height. Guys, be careful. it is released from a certain point there, from this one, going down. It is going down from a certain velocity going down, which is 11 meters, which is the height of this is what? Is 11 meters, which is actually our displacement, which is the height above the ground level from a certain point going down. All right, so this is our initial point as we are going down. So what it simply means is that the initial velocity there as we are going down, it will be a 0. But as we are moving, we do not know what's going to be the final velocity at the end. But initially, will be at 0. Then also I explained about the gravitational acceleration being 9.8 meters per square second. We are also given on our information sheet. All right, so the first question was to calculate the potential energy of the body at the point of release, which is 2 marks, the potential energy. So how do we calculate the potential energy? Remember, that's 3.1. All right, let us just have it alongside here. Okay, sorry for that. I just want this one. Just want to change this so that we do not have confusion here. Okay, let me just use this one. Okay, so that is the potential energy in this case. Remember that our potential energy is the mass times the gravitational acceleration times the height. So we have everything there. The mass in kilograms, 0.3. The gravitational acceleration of 9.8 times the height in that case, which is our height is what? Is 11 above the what? Above the ground. So that is going to give us 32.34. If you multiply this properly, that's 32.34, which is measured in what? Which is measured in joules. All right, that is the potential energy. Then we move on to 3.2, which is the kinetic energy. So they are saying the kinetic energy of the body 6 meters above the ground. All right, remember this, that the kinetic energy should be calculated over the distance that has been taken or that has been traveled, the height covered. Not to say the height above the ground or the height below or whatever. We need to consider what the part that is affected from where the object was. The object was here on top. So it is moving down. As it is moving, what is the displacement covered? What is the height covered? If this object is 6 meters above the ground, let's say this is what we have, 6 meters above the ground. Let's say this is it here. This is what we have. That one is the height above the ground, which is true. But the question is, what is the displacement covered from where it was to be at that point? What was the displacement covered? So we have to subtract 11 minus 6, which is 5 meters. This one is the most important because that is the one that is covered. So we need to know what is the final velocity when covered a displacement of 5 meters. What is the what? The final velocity. Why considering the velocity at that point? Because we know that our kinetic energy is taken from half mv squared. Remember our kinetic energy. All right. So from that, we need the velocity. We have the mass, but the velocity is the final after what has been covered. Be careful on that part. All right. So it follows that the velocity at any point, I explained that whenever you're calculating this, because if you're going down, the initial velocity is at 0. So do not waste your time. Yes, you can use v squared is equal to u squared plus 2as. You can use this to find your final velocity, but u is equal to 0. So it follows that v is simply equal to the square root of 2gs. I talked about this. That is the velocity at any point where this s is the displacement being covered, the one that is being covered from the initial point. We covered how many meters? 5 meters. So our v is going to be the square root of 2 times the gravitational acceleration of 9.8 times 5, not 6. 6 is the one above the ground, not the one that is covered. No. So if you calculate this, you are going to obtain the square root of 98. I'm just going to simplify or use that as it is, as the square root of 98. This is what I'm trying to say. If you simplify this, the square root of 2 times 9,8 times 5 like this is going to give us this 7 square root of 2. But actually this, if you simplify under without the square root like this, these numbers under the square root only like 2 times 9,8 like this times 5 like this, you get what? 98. But if you now put the square root of that answer, yes, when simplified is this, but I'm just going to use it as a single what? As a single square root. Why? Because we've got v squared. If we square, remember, if you square the square root, you get what is under the square root. So that is the advantage that I'm trying to have. So that means here, we're just going to substitute our information as it is. That is the half times the mass. In this case, remember the mass of the object, we use the mass here as 0,3. That's 0,3 times the velocity after the displacement covered, which is 98 squared. Or you can use the decimal there. It is going to be 9,899, something like that, meters per second. You can use that. All right. So this gives us the exact value of the kinetic energy, which is going to be 14,7 in what? In joules. That was the idea of the question. So you have to be very, very careful about the velocity. The kinetic energy is controlled or is determined from the velocity. So you need the velocity at each stage, the final of this from this formula, this one. This is how you're going to have your final velocity. All right. So if you check now on the last part, they are now saying the time taken to hit the ground from initial conditions, the time taken to reach the ground, the time that was taken. All right. So it follows that the time, remember, if you are given acceleration, let's take if you consider from our normal calculations, we understand that this is 3.3. Time is equivalent to the what? To the velocity, the speed over the acceleration. Like if you're given an acceleration, all right, you are simply using velocity over the gravitational. From which concept? Where did we take this from our formulas? Remember, from our formulas, we've got this formula that we stated, V is equal to U plus AT, which is our A is the gravitational acceleration. But guys, always, as we are moving from a certain point going down, the initial velocity is 0 there. So it means V is equal to GT. So if V is equal to GT, what about T? T is equal to what? Divide by what? By G by G. So it means time is V over G. Whenever you're calculating time, you can use that. It's a formula that you're supposed to know. All right? It's a formula that you are supposed to know. So that is, in this case, 3.3. Our time is equivalent to V over the gravitational acceleration. We saw where we manipulated this from. All right. So you might wonder, in some textbooks, you just see this formula and wonder, where are they taking it from when dealing with an object of this nature when it is going down? That is the idea there. You can manipulate your formulas the way that you want. Or we can use the idea of the displacement over the velocity. We can also calculate our time. I'm going to show you the other way. All right. Using this, meaning to say we are going to need the velocity at the condition when they are saying the time taken to hit the ground from initial, meaning to say to hit the ground, to hit the ground. What is our displacement this time? It's 11. We have covered the 11 meters, the whole of it to hit the ground. So like I said, V is determined from this formula. It changes. Now our V is going to change because this time our displacement is no longer the one that we had when it had covered 5 meters. This time it has covered the whole of this distance, which is 11 meters. So our velocity is going to change. The square root of 2 times what? 9,8 times the S, which is our displacement. Now it's 11 meters. To hit the ground, we have to cover 11 meters. So that was going to give us the velocity there of 14,6 83, something like that, in meters per second. So with this velocity, we can calculate our time, V over G. So that is 14,683 over the gravitational acceleration of 9,8. It gives us the time, and that was going to be 1,4982, which is 1,498 in seconds. That's how we can have our time. As long as you understand this idea of the velocity, guys, you will see that you won't have a challenge in answering of the questions. You won't have a challenge. And also, what about if we manipulate our formulas? Because we understand that we could have, all right, let us take this one. But if we check this, I think I also talked about different ways of answering this question. You can also manipulate your formula because we've got displacement, acceleration, we want time, this and that. So you know that S is equal to, remember we talked about this formula, S is equal to UT plus half AT squared, which is half AGT or half GT squared, because the acceleration is now represented by G. And I said at initial conditions, U is equal to 0. So that means we are left with S is equal to what? Half of GT squared. This is the only part that is remaining. And as we need to calculate the time, we can calculate this, cross multiply, 2 multiplies this, just multiply by 2 to cancel this, half of 2, that's what? A 1. So that's 2S is equal to GT squared. Divide by G, divide by G. That means we're going to have T squared as equal to, so this is T squared. Actually, this is T squared is equal to this value. So just leave it like that. Okay, guys, introduce the square root. I'm not going to write this stage. Introduce the square root there. So T is equal to the square root of what? 2S over G. We have manipulated. This is what we have. So that means we're going to have 2 times S, 2 times S, the displacement, which is 2 times 11 over G, the gravitational acceleration of what? Of 9,8 under the square root, So that is going to give us the time, which was taken of 1,49829 like that, which is 498 seconds, which is the same time like this one that we obtained here. So there are different ways of calculating these, different ways. As long you are putting your calculations, your formulas into consideration, the exact formula to be considered into consideration, you will see that you attempt a lot of questions with the same idea or knowledge that you are having. All right, so that was it, 7 marks on everything here. Let's check another question, which was on question 4. That was work, power, and efficiency. All right, 4.1, define torque there. So we know that the torque is the force that causes a rotation. All right, so that is, it is simply is the force. So this one is the force that causes, that causes a rotation. All right, it is the force that causes a rotation around a turning point, around a turning point. So that was the idea there. 1 mark for that, okay? Not going to waste much time there. So 4.2, you're now given that a truck with a mass of 1 ton travels at a constant velocity of 54 kilometers per hour up an incline of 20 degrees with the horizontal. All right. This is up an incline. That is a 4.2. So we have got something of this nature that is up an incline of 20 degrees. So there we've got an angle of 20 degrees. All right. So let us take note about the object. Where is it going? This object, which has got a mass of 1 ton, is going up. It is moving where? Up the incline. That is where the object is originally going, up the incline. So that is where we're going to have the total force. So that is the idea there. So given the mass of this object of 1 ton, remember 1 ton is equivalent to what? 1,000 kilograms. So there we've got a mass of 1,000 kilograms taken from an initial, because it travels at a constant, it's a constant velocity there of 54 meters per second. 54 kilometers per hour, 54 kilometers per hour. So we have got the velocity there of 54 kilometers is a constant velocity that we are moving with. So remember, how do we convert to meters per second? I talked about this. 1 meter per second is equal to what? 3,6 kilometer per hour. So just divide here by 3,6, just like the previous case, you are going to obtain 15 meters per second. The angle theta in this case, which is the angle of incline. And we are told that here on this part, right, that is with the horizontal. It is inclined 20 degrees with what? With the horizontal. So we are supposed to calculate the following. 4.21, the force to be developed by the engine if friction is what? Neglected. If friction force is neglected, if the friction force is not considered, remember, as we are going up, we are going to be opposed by two forces: the parallel component force, which is our Fs, the parallel component, and the frictional force. But they are saying the frictional force is to be neglected, is not to be considered. So we are not going to consider the frictional force. We are just considering the parallel component. All right, the idea of the parallel component, remember, there we have got the perpendicular and the parallel component at an angle of 20 degrees that we are having here. This is our perpendicular component, which is given as the weight, the cosine of theta. Then we've got the parallel component, which is our Fs. This is our same as Fs, which is W cosine of theta. And this is our W, which is equal to what? Mass times what? The gravitational acceleration. So that is the idea there. All right. So the question was to calculate the force to be developed by the engine if the friction is neglected. So as we can see, the force to be taken up by the engine as it is the force going up. It is the force going up there. So if it is the force going up, it is opposed by which other force? It is only the parallel component that is opposing, because the frictional force is not given. Remember, what goes up is the same as what is going down. Opposite there. So this one, parallel, we're talking about those ones that are in parallel. That is the idea there. So Ft is going to be equivalent to F parallel. Those ones that are in the parallel. The frictional force is not to be considered. And we said our F parallel, which is the same as this Fs, is W what? W the sine of theta. And W is equal to what? Mass times the gravitational acceleration. So there we simply have to substitute our information to obtain the value of our total force. That is the idea there. The mass of the object of 1 ton, which is 1,000 kilograms, times the gravitational acceleration of 9,8 times the sine of theta. Remember the angle there, our theta is what? Is 20 degrees. So that's the sine of 20. So that was going to give us, in this case, the total force. And that will be 3,351,797405. That's 351. 3351.797 in newtons. All right, so that is our total force. Just consider that way, because the frictional force is not there. If it was involved, then you're going to add everything. All right, then 4.22, the work done by the force in 8 seconds. What is going to be the work done? The work done. We have the force there, but we need the work done in what? In 8 seconds. So that is the question, 4.22. How do you calculate the total work done? Remember, that is the total force times the displacement, the distance, if you consider that way. So we do not have this. Where are we going to have it? All right, what do we have? We have got the velocity. Remember, it's a constant velocity. It's a constant velocity there. Guys, you know, when they write this information, read to understand here. Read to understand. It travels at a constant velocity of. What does it mean? Let's go back to our information. If this is a velocity term graph that we are now considering, not that one. On a velocity term graph, if it is a constant velocity like this, it means we are moving with, this is a horizontal line. So the velocity is constant there. It is constant. So what it means is that the displacement, as we know, that is simply the area under the graph. So it is the velocity that we have times the time, because it is under a constant what? Velocity. So the displacement is simply velocity times time. The area, length times width. The area there, length times width. So it's simply that constant velocity. What is our constant velocity? 15 meters per second. So it's going to be 15 times the time. It was constant for how many seconds? The work done in 8 seconds. So we take this velocity to be considered within 8 seconds where the work done is supposed to be taken. So the displacement must be taken within the 8 seconds. So that gives us the displacement of 120 meters. So with the displacement, we can calculate the work done, because we are saying work done is the total force that we calculated. Remember, we have got the total force of 3,351,797 times the displacement of 120 meters, force times height. That is how you can play around with this. They want you now to apply the information. Now they want you to have a proper application, not just basics. They know that we are now used to these basics. So when they're saying change of syllabus, they know it's just they want you to apply information these days. All right. So that is going to be the work done. Remember, work done measured in joules. So that is 40,000. It's actually 40. This is 402,215,64, something like that in joules. So you can divide by 1,000. That's 402,21. Gonna round off, gonna be a 6 in what? In kilojoules. All right. That is the work done. Actually, the total work done in that period, in that time frame, for that particular time frame, that will be our total work done. Then they want us to calculate the power developed in kilowatts. In how many seconds? We are not given the time. So we are considering the time that we used before, because here we're supposed to be given the time. So we are using this work done within the same time frame that we are given. Remember, power, I explained that power is simply what? Work done per second. That is the idea of what? Of the power. All right. So that's 4.23. So the power is simply work done per second, which is work done over time. Isn't it, guys? Kilojoules per second. That's power. The work done that we calculated within, since the power is needed in kilowatts, it means we've got kilojoules per second. So you're simply going to use our work done in kilojoules, 402.216 kilojoules over the time frame in the 8 seconds time. Work done per second, like I'm saying, the time was 8 seconds there. So if we divide, that was going to give us 50,277, something like that, 277, which are, these are kilojoules, these are seconds. So it's going to be kilojoules per second, which is what? Which is kilowatts. So that is your power in watts, in kilowatts. Is it the only way of calculating this same power? No. We can calculate our power from where? We can calculate our power from the total force. So this could be another way. Power is equivalent to the total force in that case times the velocity. Are we having the total force? We've got the total force that we calculated here. Remember our FT, which is the parallel component, which gave us 3,351,797 times the total velocity, which is the velocity for that time frame of what? Of 8 seconds. What was the velocity? The velocity there, it was that initial. Remember, it was a constant velocity, does not change. 15 meters per second. So that means we're going to multiply by what? By 15. So this is going to give us 50,2769. So it's going to be 277 in kilowatts, right? If you convert to kilowatts, but before it is like this. Let me take the first value first. It was going to be 50,276.955, which will be in watts. So convert to kilowatts, that's 50,2769, which is 77 kilowatts. Remember, the power was actually, we are actually told to give this in kilowatts. It's an instruction in kilowatts. you're supposed to use what you're given. That's why I'm converting this to what? To kilowatts. All right. So that was our question 4.23. All right. Then another question, which is 4.3. So on 4.3, we are given, in this case, a flywheel. All right. So this is the condition of a flywheel. That is, let's see. The turning force applied to a flywheel is 1,600 and 1,650. The moment we are talking about the turning force, it means we are supposed to think about the torque there. And we are given the diameter of the flywheel as 350 millimeters. So the diameter, if we convert this to meters, divide by 1,000, that's 0.35 in meters. So the question was to calculate the torque of the flywheel. All right, the torque, remember, torque is what? The force that we are given times the perpendicular distance, which is the radius. All right, so that is how you could have calculated this 4.3. All right, so that is 4.3. We are simply saying the torque is the force times the perpendicular distance, which is what? Which is the radius. We have the force of 1,650 times the radius. Remember, the radius is the diameter over 2. The diameter that we are given in meters, which is 0.35 over 2. So this is going to give us the torque. So that's we are going to obtain 288.75, something like that. All right, that is Newton meter. So this is how persons are given. All right, this is how your questions are given. You have to be very, very careful how you attempt your question. As you can see, that is 10 marks on question 4, which is actually fine. We just have to make sure that we collect all those marks in our next examinations for those who are writing for the next time, and for those who are writing for the first time for this subject of Science N2, you're supposed to collect all these marks. So the next part, the 5, was question 5, which is 5.1 on mechanical drives and lifting machines. All right, state 3 disadvantages. Take note, read the question properly. All right, we need disadvantages of what? Of the gear drives. All right, so one of the disadvantages that we have, they are expensive to manufacture. All right, so they are expensive to manufacture. All right, that is what we have. The other thing, expensive to repair. So it's actually they're expensive. Everything there is expensive. Expensive to repair. Then the other thing, require constant lubrication. So they require constant lubrication. All right, lubrication. That is the idea there. And also the driving and the driven shaft must be closer together. All right, that is the driving and driven shaft. The driven shaft, all right, must be close. All right, must be closer. All right, together. All right, must be close together or closer. Let's just say close and close together like that. So these are some of the disadvantages that we can have when working with what? A gear drive or with gear drives. All right, 4.2 as on a chain drive. If we check that question properly, they are saying a chain drive has a driving pulley with the 45 teeth and the driven pulley with 90 teeth or teeth and so forth. All right. So remember, guys, the condition of the driver, driven, and so concept 5.2. All right. So I'm just gonna use the driver. All right. The driver as 1 and the driven as 2. All right. The driven, just gonna take this as what? As my 2. For more of this, check the separate video on this as a separate, like as a separate topic, mechanical drives and lifting machine. This same question paper explained even with the diagrams and so forth. So then we are given the teeth, the number of teeth on the driving. The driving is the one that has got 45. So that's T1. Remember I said the driver, it's 1. So I've got T1 here, or you can use TD. I don't know the way that you want to apply or to use, but I'm just gonna use 1. So that is 45. And what else do we have? then a driven with 90 teeth. So the driven T2, the number of teeth on the driven, that's T2 there. It's 90. What else? The rotational frequency of the driving pulley, 660. All right, so the driving, which is the speed here, N1 on the driving, 660 revs per minute. And on the driven, we do not have the speed there. That is the one they are asking us here to calculate that rotational frequency of the driven pulley, but in what? In revs per second. So it's either we are going to first change this rotational frequency that we're given the speed first to revs per second, or we are going to use as it is, then we convert on the final answer. All right, so I'm just going to use as it is. Remember the relationship between the speed and the number of teeth that states that the product of this N1 T1 is equal to N2 T2. If you use A and B, NA TA is equal to NB TB. I don't know how you're going to present this, as long as you understand what you're writing there. So you said 2 represents the driven, so we need the speed on the driven, which is this N2. So how can we find this? We can simply divide by T2, since we are multiplying, divide by T2 here. That means the speed N2 on the driven is going to be equal to N1 T1 over T2. So there, let us substitute our values. N1, which is the speed, like I said, this is in revs per minute. So our answer is going to be what? In revs per minute, times T1, which is 45, times T2, which is 90. This gives us the speed, the rotational frequency there of 330 revs per minute. So this is 330 revs per minute. But the answer, according to the question, they need this in revs per second. Revs per second. So a second from a minute, we understand that a minute is equivalent to how many seconds? 60 seconds. So to convert these to seconds, we have to use 60. So N2 is going to be 330 revs over 60 seconds. So that our answer is going to be revs per second. All right, so that is the idea there. We divide by what? By 60. So that is going to be 5,5 revs per second. So that is the speed that we are having in that case. Okay, let's consider the other question. 5.22. Now calculate the velocity ratio of the chain drive. All right, remember we've got this formula. When you are considering the velocity ratio from our speed, we can use the speed. That's 5.22. The velocity ratio is simply the speed on the driven over that speed from the driver in this case. All right, that is the driven N2. So it's going to depend. Are you going to use revs per second or revs per minute? All right. Since N1 on the driver is revs per minute, as we saw here, it's we used this as revs per, we never converted to revs per minute to revs per second. So you're just going to use the revs per minute. It's an advantage. N1 it's 660. N2 in revs per minute. Remember, this was the answer here in revs per minute, 330. So that's N2, 330 in revs per minute over N1, which was 660 revs per minute. That's going to be 1/2. That's, you can write even as 1:2 like this, the velocity ratio. So that was the idea of the question. Let's consider another part. 5.3, we are given a differential pulley block in this case. All right, so we've got a differential pulley block. You must also understand your diagrams and so forth. All right, but there we are given it has got an efficiency of what? 75%. So the efficiency of this is at 75%. And has a mechanical advantage of 20. The mechanical advantage there is 20. And the larger pulley has got 30 slots. So we're given the number of slots, and this is for the larger pulley. I'm just going to use the capital letter S, which means we do not have for the smaller one. Some they use N for the number of slots. All right. So it depends with what do you want to present. So the first question was calculate the following. 5.31, the load that can be lifted by an effort of 800 Newton. That's 5.31. All right, so 5.31, we are given the effort there of what? The effort of 800 Newton. So the effort is 800 Newton. All right, that is 800 Newton. And the question is, we are supposed to calculate the load from this. All right, how can we calculate the load? What can give, what can consist of the effort and the load at the same time? Is there anything from what we are given here that includes the load and the effort? It is there. What is it? The mechanical advantage. We understand that the mechanical advantage is the what? The load over what? Over the effort. So if it is the load over the effort, you're just going to substitute. What we have is the mechanical advantage 20 is equal to the load, that is the one that we are supposed to calculate, over the effort of what? Of 800 Newton, which is the one that you're given there. So you're going to cross multiply 1 times the load. That is the load is equal to 20 times 800. If you multiply this, what are we going to obtain? 20 times 800 is 16,000, which is 16,000 Newton, or 16 kilonewton. So just going to write as 16 kilonewton. That is the load in this case. Okay, that is how we could have calculated our load. Then the displacement ratio of the pulley block. The displacement ratio is the same way as the way that you calculate your velocity ratio. So you could have taken advantage of what now? Because we have efficiency here. We have the mechanical advantage, and we want velocity ratio, which is the displacement ratio. You can use those two. All right, 5.32. The displacement ratio, I'm just going to write it as what? As the velocity ratio, so that we do not have a confusion. Mechanical advantage over the velocity ratio times what? 100%. So in this case, our efficiency as a percentage is 75, right? So that is 75 is equal to, we have the mechanical advantage of what? Of 20, but we do not have the displacement ratio times 100. So we're just going to divide by this 100, which is for the percentage part. So that's going to be 0.75 is equal to 20 over the displacement ratio. So as we can see, guys, this is an equation that we have formulated. We are back to our mathematics, cross multiply. 0.75 times VR, that's 0.75 times the displacement ratio, 1 times 20, which is 20 there. So you're going to divide by 0.75, divide by 0.75. So this will cancel. We have our displacement ratio as 20 over 0.75. So if we divide this, that was going to be 26,6666, and so on and so on and so on and so on. So we can even approximate this. Let us just approximate to the nearest whole number as what? As a 27, all right? Which is fine. You can even leave it like that. Okay. That was our displacement ratio. Then from here, they want us to calculate the number of slots in the smaller pulley. The number of slots, which is this S here, in the smaller pulley. So we are supposed to formulate an equation that consists of that S. Remember, from the displacement ratio, we understand that it is the ratio that is taken also as on its own. This same displacement ratio on its own is given as the 2 times the number of slots on the larger pulley over the difference, which is the larger one minus the smaller one. We have this velocity ratio from our calculations, which is our displacement ratio, as 27. So that's 27 is equal to 2 times the number of slots from the larger pulley, which is what? Which is from the larger pulley. Remember, you're given the number of slots is what? Is 30. So that is a 30 in that case. So it's 2 times 30 over the difference, 30 minus S, which is S is from what? The smaller, this small letter S is from the smaller pulley. It's an equation that you have formulated that you need to solve. All right. So that is 27 over 1 is equal to, gonna have this as 60. So that's 60 over 30 minus S. So in order for us to calculate for S, it's either you're gonna cross multiply or you're gonna make whatever that you want the subject. So if we cross multiply this part here, we're gonna have 27 into 30 minus S, which is equal to what? 60. Multiply by 27. You're gonna, if you want to expand by 27, it's up to you guys. Gonna expand by 27, which is 810. So this is 810 minus 27S is equal to 60. So minus 27S is equal to, transpose this to the other side, it becomes a negative on this side. So that is, we're gonna subtract that, which is gonna be minus 750. All right. So to find S in this case, we divide by what? By negative what? By negative 27 both sides, which is gonna be something like 250 over 9, which is simply 27,77777, and so on and so on. So in terms of the number of slots, how many slots do we have? It's gonna approximate to the nearest whole number there. That will be at 28. So you approximate that to the nearest whole number. 7 is gonna change this 7 into 8. That is the number of slots that we're gonna have at the end. Is how many slots? 28 slots from the smaller pulley. You see, that's how you answer your questions. You have to apply the formulas. Which formula is appropriate? How can you manipulate that formula into what you are supposed to calculate? What are you supposed to calculate? How can you manipulate the formula? That is the idea. Okay, so let's check the other part. We are now having here on 4.4, 5.4. 5.4 is define the SI unit of the Pascal. So the Pascal is simply the measure of what? The measure of pressure, which is 1 Newton per what? Per square meter. This is simply the measure of what? The measure of what? Of pressure. All right, that's the Pascal. All right, 5.5, name 3 factors for determining the pressure exerted by a vertical liquid column, taken at a perpendicular height, that is the vertical point. What is it that affects that pressure? Remember, the pressure at that condition is the density times the height times the gravitational acceleration. So it is affected by what? The density. These are the factors that affect, which is the density of what? Of the liquid. All right, we're going to talk about the density of liquid. In this case, we have got what? The gravitational acceleration. So it's going to also be affected by the gravitational acceleration. All right, we've got the gravitational acceleration. What is it again? The height. It's going to be affected by the height, which is the vertical liquid column, which is the height of what? Of the liquid column. These are the 3 factors that are going to affect in this height in what? In meters. That is the idea there. Just like that. All right. So 17 marks on everything. All right, let's check another question, which is question 6, which was on friction. Define the term friction. What is it that you understand by the friction? So friction is simply the resistance to relative motion between 2 surfaces or between surfaces. So this one is simply the resistance. All right, so this is the resistance to relative motion, motion between 2 surfaces. All right, between 2 surfaces. That is the idea of what? Of the friction. Then 6.2, we are given that a train weighing, this is the weight, 700 and what? And 84 Newton is being pulled up. It is going up the incline, all right, which is inclined at an angle of what? Of 23 degrees with the horizontal. The coefficient of friction, once we are given the coefficient of friction, it means there is a frictional force. So this time we shall see the diagram is going to be different, a little bit different from that one that we had when we had a similar part of this diagram. Remember, we drew a similar diagram, but there we were told to neglect the frictional force. Here it's involved because we are given what? We are given the coefficient of friction. Remember, it's inclined at an angle of what? Of 23 degrees, and this is going up as we are given. This is going up. So as it is going up, we do not know what is going to be the total force when going up. But as we know, this object is going to be opposed by two forces, which is the frictional force and the parallel component in that case. These are the two factors that are going to affect, all right, as we have got our weight component in this, well, weight, and this is perpendicular parallel, all right, like this. This is our perpendicular, which is weight cos of theta. This is our parallel, which is weight sine of theta. Like I said, you can use F perpendicular like this, F parallel like that. All right, this will be at 90 degrees, this at 23 degrees, and this is our weight. And we have the weight of the object, which is what? 784. We already have this weight. Our weight is given as 784 Newton. And we are told that is going up. That is why this is the one that is on top. And these are the ones that are opposing that side. Because if it is going down like this, these are going to be on the other hand. They will be opposing on the other hand. The frictional force is going to be opposing on the other hand. So we are given also the coefficient of friction between the plane and the wheel of the train, which is 0.3. The coefficient of friction, 0.3. All right, so the question was on 6.21. All right, let's check this one here. That's 6.21. The weight component perpendicular to the sliding plane. The weight component perpendicular, which is this one. The one perpendicular, this one FC, or F perpendicular, the same way that I said you can present this way. I don't know the way that you're going to put it that way. All right, so 6.21, the weight component perpendicular is going to be W cos of theta. We have W as it is. There's no need for us to use mg because already we are given the weight. 784 times the cosine of the angle of what? Of 23 degrees. That was going to give us 721.675. This is 6758, which is 676 in Newton. All right. Then 6.22, the weight component parallel to the sliding plane. This one is the parallel one. This is the one parallel, W sine theta. So meaning to say 6.22, the one parallel is W the sine of theta. Already we are given our W there, the weight 784. So this is 784, the sine of what? The sine of theta. Our theta is what? 23 degrees. All right, so that was going to give us 306,332, which is 33 in what? In Newton. That is the parallel component, or you can write it this way. It's just one and the same thing. Okay, then the frictional force. Remember, we are given the coefficient of friction, so we can be able to calculate the frictional force. And like I said, from the coefficient of friction, maybe, okay, let us just even write it here. I said from the coefficient of friction, it states that it is the frictional force over the what? The perpendicular component if you're dealing under the friction. So in order for us to have the frictional force, this is same as over 1. So you're going to cross multiply 1 times the frictional force. That's the frictional force is equal to the coefficient of friction times what? The perpendicular component. So in this case, we're going to take our coefficient of friction. That's what? 0.3. So you're going to have the frictional force, which is the coefficient of friction, 0.3 times the perpendicular force that we are given here. That's 721.676. So this is 721.676. And that was going to give us the frictional force, which is 216,5028, which is 503 in what? In Newton. All right. So this is the idea that we are supposed to simply have or obtain in this case. All right. Then they want us to calculate the external force required to pull the train up the plane. As we can see, there is a force here that is going up, this one, which is opposed by these two forces. So as we know, what is the other part? should be equal to what is opposing on the other end. So you simply have to add these ones to find this one that is going up, which is our FT, which is the one that is going up. So that means 6.24, we saw what is going up is the total force. It's opposed by the frictional force and what? The parallel component. We calculated the frictional force, 216.503, plus the parallel component. We calculated our parallel component, 306.33. All right, so this is just going to be added, 306, that's 306.33, like that. So that is the force going up, which is the total force, 522.836 in Newton. That is the idea there. All right, I hope we are together. That was just 9 marks there. Okay, then question number 7 was on heat. Name the instrument used to measure the body temperature. So we deal with what? A thermometer. A thermometer is the one used there to measure the body temperature. Then 7.2 we are given now that name 3 factors that will influence the change in length of a metal. The change in length. Remember, this is taken from the formula. The change in length from our formula sheet is given as the original length times the linear coefficient of expansion of that same material that you're talking about, or metal, times the change in length. So these are the factors that affect. You take from the formula, what is it? The original length. So you're going to be affected by the original length of the what? Of the metal. All right, this is the first factor. Then we have got what? The coefficient of expansion, the type of metal that we are talking about is determined by this. That is the linear coefficient. We've got the linear coefficient of what? Of expansion, because it must expand. All right. Then the temperature, that is the change in temperature, or temperature change. The change in what? In temperature. Or simply the temperature change. That is the idea there. Okay, so that is our question. 7.3, we are now given on 7.3. This is a mass, 7.3. Calculate the mass. So there we need to calculate the mass of a coal required to heat 500 liters of water. All right, so we need, there's coal here. We need the mass of coal. We do not know, but there is something about water there. All right, required to heat. So the coal is heating up the water, which has got 500 liters. Remember, the mass of water, 1 kilogram is equal to 1 liter. So it means we are also given the mass there of 500 kilograms. From this temperature to 90, so the change in temperature is given from temperature 1, 8 degrees Celsius, up to what? 90 degrees Celsius. That is our final temperature T2, 90 degrees Celsius. And there we are given, if there is no heat loss. If there is no heat loss. If there is no heat loss, what does it mean? All right, if there is no heat loss, guys, you are going to see that the energy here is going to be the same. Remember how we obtain the energy, which is the energy for coal. We are going to have the same energy, the energy that we are using to heat the water. The energy that we are using to heat the water is the same, because there's not going to change. We are going to, at that condition, as we know that this Q for coal is the mass times the heat value. So we have got the mass there times the heat value is equal. For water, it is given as the mass times the specific heat capacity. If you check from our calculations, we're going to need the specific heat capacity of what? Of water times the change in temperature. So that means in this case, to obtain this mass of coal, we can simply divide, by the heat value of coal. The heat value, the heat value. So this is it. Remembering this M here is for coal. Let me just write as MC to represent the coal. All right. Or you can calculate this separately, you get your answer, then you divide, all right? But I'm just gonna combine this. So the mass of coal is gonna be equal to the mass. This one is the mass of what? The mass of water. Remember, here we're considering water. And what is the mass of water? The mass of water is 500 kilograms. So that's 500 kilograms in that case, right? 500 kilograms. Sorry for this, guys. So that's going to be 500 times the specific heat capacity. If you check from your information sheet, the specific heat capacity was 4187 times the change in temperature, meaning to say T2 minus T1. So this one you check on the information sheet on the first page. There you check there is 4187 there for water. The change in temperature, that's T2 minus T1, 90 minus what? 90 minus 8. So that is going to be the difference there, 90 minus 8. Everything over the heat value, which is the heat value of coal. Remember, we are talking about what? We are talking about the heat value of coal. So from your information sheet, again, we are going to see that we are given that value. The heat value of coal is given as 30 megajoules per kilogram. That is 30 megajoules is to the exponent of 3. So this is going to give us the mass of coal. This is the heat from water divided by the what? By the heat value of what? Of coal. We just made this the subject. Okay, so let us just see what we're gonna have from our calculator. All right, let me just show you this part, guys. All right, so this is it. Let's simplify. That is going to be 500 multiplied to 4187 times the difference there, that's 90 minus 8. 90 minus 8, like this, over 30 megajoules, 30 megajoules per kilogram. That's 30 times what? 10 to the exponent of 6, which is going to give us 5,722 like that. You can even round off to 3 decimal places direct on your calculator. That is shift, set up, then you fix this to 6 to 3 decimal place, press 6. Your answer is going to be 3 decimal places, 5,722. That's 5,722 kilograms. Remember, this is the mass that we are calculating. So it's going to be in what? In kilograms. So that was the idea of the question there. This is how we answer our question. Since the heat is not lost, it means we are having the same heat for coal and for water at the end when the temperature is at what? At 90 degrees Celsius. All right. Then on the other part, we are given 7.4, a steel door. So there we are dealing with a steel. All right. That's a steel door that we are talking about there. That's 7.4. If you check for steel from the information sheet, if you check the linear coefficient of expansion for steel, it's 0,000 something like that, 0.12 per watt per degree Celsius, like that, which is taken. So there we have got a condition that we are supposed to consider. All right, for the linear coefficient of expansion of what? Of steel. This is our linear coefficient of expansion from the information sheet, like I said. So we're given that it has a height, with a height, in this case, the height of this door is 2,2 meters. The width of this door is 0,7 meters, is manufactured at a temperature of, that is the original temperature there, at 13 degrees Celsius. That is, these are the initial conditions of our steel door. These are the initial conditions, our starting point, where we started from, initial values or initial conditions. All right. So now they are saying, if the temperature of the steel door increases, meaning to say we are now at the final conditions where T2 is now at what? At 36.7 degrees Celsius. Calculate the change in temperature. All right, what is going to be the change in temperature? 7.41. So the change in temperature, remember, is simply T2 minus T1. All right, so you're just going to subtract our temperatures, in this case T2, that is 36.7 degrees Celsius, minus T1, which is 13 degrees Celsius. That will be 23.7. That's 23.7 degrees Celsius, the change in temperature. Okay, then the change in height of the steel door in millimeters. In millimeters. The change in what? In height. No, not the change of the width. No, the change in height. Only the height there. Remember, we considered about the change in length, and I said if it was to calculate the change in length, you are going to use the same formula. The change in length is equal to the original length times this times this. This is what you know. But there we are talking about not the length, but the height. But height and length, they've got the same properties. We are still talking about something that is measured in the same units, same thing. So it is going to be the original height times the linear coefficient of expansion times the change in temperature, which is in this case, we have the original height from the initial conditions that we are given here. That is where we have the original height. But the original height is in meters, whereas the answer is needed in millimeters. So it's either we are going to change this or we are going to change on the final answer. All right, I'm just going to use the height in meters. Remember, this is in meters, 2,2. So that is 2,2 times the linear coefficient of expansion of what? Of steel. This is a steel bar. This is a steel door. So I said, if you check from your information sheet, it is given from the first page, actually, it is given as 0,00012 times the change in temperature. Already calculated the change in temperature here. T2 minus T1, we got 23,7. So that is, we are going to obtain the change in height. And the answer that we're going to have will be in meters. All right, remember this was used in meters, so you're going to get 0,00 something like that, 62568 in millimeters, like that. In meters, I mean. So to convert to millimeters, you simply multiply by 1,000. Remember, 1 meter is 1,000 millimeters. So if you multiply by 1,000, it will be 0,626. That will be 0,26 in millimeters. This is the change in height. The change in what? In height, in millimeters. Okay? Then on the other hand, on 7.24, the height of the steel door now at the temperature of what? 36,7. This is the final, at this temperature, this is our final temperature now. 36,7. So the height at this temperature is the final height there. How do we calculate the final values? Is it final length? Is it final height? The final height is the original plus the change that happened in that height. So that means in this case, 7.43, the final height is going to be the original height plus the change in height. So it's now depend with the unit of measurement. Are you going to leave your answer in meters or millimeters? If you are using millimeters, we have to convert the original height to be in millimeters, 2,2 meters. Remember how we convert meters to millimeters, we multiply by 1,000. So the final height is going to be 2,2 times 1,000 to convert to millimeters, plus the change in height that we already have of 0.626, which is already in what? In millimeters. That is the final height in millimeters was going to be something like 2,200,626 in millimeters. All right? You can consider that. You can consider millimeters. In meters, it's up to you. If you consider meters, we use these original values that we had before. So I want you to do that and see what you're going to have. But these are the typical questions that you might have concerning the heat, So you need to understand your questions, how to attempt these typical questions. All right, then we move on to the other part of the question. In this case, we are given on question number 8, it was the particle of structure of atomic matter that, okay, so this one, it was affected here. I don't know what happened there. All right, anyways, they were supposed to indicate whether the following statements are true or false. All right, 8.11, when salt dissolves in water, the sodium and chlorine ions of many molecules become separated. That phenomenon is called a solvent. This is actually true. That is exactly what happens if we are dealing with what the sodium and chlorine in water. All right, it's gonna be the sodium and chlorine. They will be of many molecules. All right, that is exactly the definition that we have there. 8.12. If an atom gains electron, it has a negative charge and is all right. It has a negative charge, which is true, and is known as an anion, which is actually true. All right, this is true. All right, 8.13, the change, right, the charge of the nucleus in an atom is positive. All right, remember the nucleus, we only consider the protons there, which is what the one that are important. So the charge that we can talk about is what is positive, which is actually true. Distilled water is a good conductor of electricity. This is what? This is false. All right. This distilled water is not, but that does not. So this is the consideration. It does not contain any dissolved salts. All right. So it is a poor conductor of electricity. It is not a good conductor, this, because it does not contain any dissolved salt. But as long as we are with water, guys, do not play with water, no matter if we are saying it's not a conductor. But when it comes to water, never play with water and electricity at the same time. What is the charge of the cathode in an electrolysis process? So the charge of the cathode, it's a negative, all right? So this is a negative. It's taken as a negative. That's the cathode. The anode is the one that is taken as what? As the positive. Positive is anode, cathode, negative. All right. 8.3, name 3 examples where electroplating is used. Examples. We can talk about in terms of the sink taps, where we are talking about these sink taps that we talk about, that we have the pots, the car parts. They use these electroplating machinery in our industries. They use these electroplating. So there are so many conditions where electroplating is used. Remember, we are just avoiding that issue or that idea of what corrosion to happen. We want to avoid that. So we can have, as long there's a metal object. All right. Then electricity on question 9. A 2 ohm resistor is coupled with a 6 ohm. So we've got a 2 ohm and a 6 ohm in parallel. Remember, in parallel. Determine the value of the single resistance that we have the same resistance as the parallel couple. So remember, in parallel, how you find your total resistance, the product over the sum. If there are 2 resistors, we can use what? Product over sum. That is the total. That will be the total resistance there. 2 times 6 over 2 plus 6, product over the sum. All right, so this is gonna give us something like 1,5 ohm, or we can use this formula that in parallel 1 over Rp, or 1 over Rp is equal to 1 over R1 plus 1 over R2. So it's 1 over R1 plus 1 over R2, and so on and so on. So you can use this and see if we're gonna have the same answer for Rp. All right, that means we're gonna have 1 over 2 plus 1 over 6. All right, what are we gonna have? Let's just quickly check this on our calculator. That's 1 over 2 plus 1 over 6. 1 over 6 like this, which is 2 over 3. So that's 2 over 3. That's 1 over Rp. So to find Rp, you just introduce 1 over this, we get Rp. 1 over this, we get the answer there. So it's just simply 1 divided by that answer, the reciprocal, the inverse. So that will be 1,5 ohms in that case. All right, that is the parallel resistance that we are having there. So many ways, guys, of killing a cat, as you can see, or so many ways of simplifying this. Okay, on 9.2, calculate the total resistance of the circuit shown in Fig 2 above. All right, so if we consider our diagram, we can see that there is a series combination here. So we're going to combine that RS, R1 plus R2, we add 3 plus 4, that will be 7 ohms. Then after combining this, we are left with the parallel. So we said in parallel, if there are two resistors, you can simply use product over sum. So that's 7 times the resistance of 32, the product over the sum of 7 plus 32. Remember, the 7 is the one that we now have. We have combined this to be a single resistor now. It is a single resistor, this one, of what? Of 7 ohms, like this. So we are now just left with that, just like the couple that we had previously here. They were in parallel. So we use the product over sum. So that's our RP from this calculation. All right, let us just see our calculator now and what are we going to have here? All right, so where am I putting the negative? That is 7. Going to have a fraction here, 7 times 32. 7 times 32 over 7 plus 32. 7 plus 32 like that. Product over sum. So that will be 5.77 like this to 3 decimal places. Remember, I fixed my calculator to 3 decimal places. That's 5.744. 5.744 ohms. So that was going to be the total resistance of our combination of that circuit that we are given there. All right. Then on 9.3, we are now given name 3 factors that will influence the resistance of the conductor. Remember, I said from the formula, whenever they're saying name these things that affected this name, take it from the formula. What is the formula for resistance? Resistance is rho L over the area, resistivity times length over the area. So what are we talking about? The resistivity there, the type of conductor. So meaning to say factors that we are talking about is the resistivity. From the resistivity, we are talking about the type of what? The type of the conductor. All right, that we are going to apply. What is it here? The length of that same material or conductor. So we talk about the length of the conductor. Then the cross-sectional area. Also talk about what? The cross-sectional area of the conductor. These are the factors, the length in meters, the cross-sectional area in square meters. That is the idea, the cross-sectional area. Okay. Then in this case, 9.4, make a neat sketch, all right? Make a neat sketch labeled drawing of apparatus that may be used to demonstrate electromagnetic induction. I said, guys, as for me, when it comes to diagram, I'm not that good, but I'm just going to have a sketch, something of this nature. Remember, I'm going to have a coil inside here, north and south pole. So let us just say this is our north and this is our south, and a galvanometer. All right, so you're gonna have a galvanometer for our readings here. Let's just put it outside like that. Then now this coil now is supposed to be taken in. All right, just gonna have the coupling part. Okay, something like this. Okay, something like this up to the end when it joins back here. Okay, so that's it. The reflection, I mean, remember the north and the pole will be north and south pole will be tending to attract. So we shall have these forces of attraction from these 2 points. All right, so that's a simple sketch that you can just have. The guy is just a simple sketch there that you need. 9.5, they need us 2 examples where mutual induction is used in practice. We've got transformers there, 9.5. We've got an application of transformers. All right. We have got electric motors. We've got electric motors there. We have got generators, right? We have got the generators also. So many. 9.6, briefly explain the term self-induction. All right, I'm just going to say this one, then you're going to just try and work on it. All right, so self-induction is the generation of an EMF. The generation of an EMF in a circuit by varying the current in that same circuit. All right, we talked about this, all right? That is the self-induction part. So that was our question, guys. Just 1 mark, guys. 13 marks and everything, then a total of 100 marks in this question paper. So like I said, for you to understand each and every topic properly, make sure that you watch separate videos that is on electricity, on dynamics, on this, on the same question paper. I recorded those ones so that you can have a deeper understanding. This one, guys, I'm answering a question paper for you to understand the basics, but for you to have a deeper knowledge on each and every topic, work on that topic as a separate, so that you can have full information on what and how to answer many questions pertaining the same topic, or same questions under the same topic that you're talking about. All right, guys, that's what we had on this platform from Maths Zone African Motives. Till we meet again.